Good morning, everyone. Hope you are all doing fine. Today's lecture will deal with alcohols. What are alcohols? Alcohols are compounds that have an OH group attached to a carbon, an aliphatic carbon. If the carbon is an aromatic carbon, these are phenyls. And these are not the target of this lecture. However, if the OH is attached to a carbon, then these are alcohols. The aliphatic carbon plays an important role, the type of aliphatic carbon plays an important role in the classification of alcohols. If the OH group is attached to a carbon which is attached to another carbon, then this is a primary alcohol. If the carbon attached to the OH is attached to two carbons, then this is a secondary alcohol. If the carbon attached to the OH is attached to three carbons, then this is a tertiary alcohol. So it all relies on the carbon attached to the OH. If it's a primary carbon, then this is a primary alcohol. If it's a secondary carbon, then this is a secondary alcohol. If it's a tertiary carbon, then this is a tertiary alcohol. Why didn't we refer to the functional group itself, the OH itself, how many carbons it is attached to? Because the OH is monovalent. It is attached to only one group. So we cannot use this function group to classify them according to primary and secondary and tertiary. So we go to the carbon, so we look at the carbon attached to the functional group. If we have any functional group which is monovalent functional group, to classify the class of compounds, you look at the carbon attached to this functional group. If it's a primary carbon, then this is a primary functional group. If it's a secondary carbon, then this is a secondary functional group. And if it's a tertiary carbon, then this is a tertiary functional group. Another classification that we have for the alcohols is relying on the number of OHs available in the compound. If we have one OH, then this is a monohydric alcohol. If we have two OHs, then this is a dihydric alcohol. If we have three OHs, then this is a trihydric alcohol. The most famous example of trihydric alcohols is glycerol. An example of a dihydric alcohol is ethylene glycol. And the monohydric alcohols are all the alcohols that we will deal with, whether primary or secondary or tertiary alcohols. Okay? So this is the classification of these compounds. As we said, if you have one OH group, then this is a monohydric alcohol, which can be classified into primary, secondary, or tertiary based on the number of carbons attached to the carbon attached to the OH. The second class is the dihydric, which has two OHs, and a very famous example is the ethylene glycol. Finally, if we have three OHs, then this is a trihydric alcohol, and your famous example is glycerol. If we take a look at the nomenclature of the monohydric alcohols, we have, as usually used to study, we have the common names and the EUPAC names. We are used to look at two types of nomenclature, common names and EUPAC names. In case of alcohols, the common names is something like, for example, ethylene glycol. This is a common name. Glycerol is a common name. This is in case of more than one OH. How about if we are dealing with a monohydric alcohol? It will rely on naming the alkyl chain attached to the OH and then putting the word alcohol. So it's alkyl alcohol. For example, if you have one carbon, then this is the methane. It's going to be methyl alcohol. If it's two carbons, then this is the ethane. We say that this is ethyl alcohol, and so on. As for the nomenclature of these compounds, you have one common rule in case of nomenclating EUPAC any class of organic compounds, which is you look for the longest chain containing the highest priority functional group. You name the alkane that has the same number of carbons, and then you number the compound from the side nearest to this highest priority functional group. Okay, so something like that. How many carbons do we have? We have 1, 2, 3, 4, and 5. So this is a pentane. And in case of this compound, your highest priority functional group is the alcohol. You remove the E at the end of the alkane and you add an ol. So this is pentanol. One last thing is that you have to specify the position of the OH. So this is a 1, 2, 3. By the way, if you try to number from the other side, again, it's going to be 3. So this is the 3-pentanol or pentane 3-ol. Both are correct. You can put the number at the beginning of the name, or you can put it just before the suffix of the functional group. Suppose that your your alcoholic group, the OH, is not the highest priority functional group. For example, if you have an acid in your compound, this is a higher priority functional group than the alcohol. How are you going to nomenclate such a compound? This is the acid. It has 3 carbons, so this is the propanoic acid. And then you number from the nearest side to the highest priority function group, which is the carboxylic group. It's going to be 1 and then 2. So this is the 2, and then you say hydroxy. So if it's a higher priority, it's going to be an ol at the end of the name. If it's of a lower priority, then it's going to be a hydroxy at the beginning of the name. This is what we have just mentioned, how to nomenclate these compounds. As we said, the common name is that you say the alkyl group and then you put the word alcohol. The EUPAC, you choose the longest chain containing the OH if it's the highest priority functional group, and you start numbering to give the OH the least possible numbering. You remove the E at the end of the alkane and you put an ol in its place. If the OH is not the highest priority functional group, then it's going to be named as a hydroxy group. Now, if we study the preparation or the synthesis of these compounds, they can be prepared by 4 different methods. If you have an OH that you need to introduce, you can actually start from alkenes, where you have a doubly bonded carbon, and you hydrate these compounds, whether Markovnikov or anti-Markovnikov. You will end up introducing an OH to your compound at the position depending on whether it's Markovnikov or anti-Markovnikov. So this is the first method. The second method is that you can have an alkyl halide that you substitute by a hydroxyl group and end up having an alcoholic group. The third method is that you can oxidize aldehydes, you can oxidize aldehydes or carboxylic acids. By oxidation, you can end up with by reduction, you can reduce these compounds. These are the higher oxidation. So by reduction, you can reduce these compounds to end up with the alcohol. And then finally, you can have the Grignard reagent. You can use Grignard reagent on aldehydes or ketones. If you react them with Grignard reagent, you end up with the tertiary alcohol. Let's discuss each of these methods. So first of all, we said that if you have an alkene, you can add a molecule of water and you end up with the alcoholic compound. You can use the regular hydration. You can use the oxymercuration, demercuration. Both these methods are Markovnikov additions, where the H goes to the carbon that has more number of hydrogens. Or you can hydroborate them. You can use the hydroboration to end up with an anti-Markovnikov method. For example, if you have this compound, you will get the OH at the terminal carbon, which has more hydrogens. So this is how you can prepare alcohols from alkenes. When you try to prepare them from alkyl halides, you react the alkyl halides with a strong nucleophile, which is the hydroxyl group, substituting the halogen and introducing an OH in its place. The third method is that the reduction of a higher oxidation compounds. For example, you can oxidize aldehydes. You can reduce aldehydes. You can reduce acids, and you can reduce acid derivatives such as acid halides or esters. All these compounds, if you reduce them, you will end up with the alcoholic compounds. Finally, we have the Grignard method. Finally, if we deal with the last method for the preparation of alcohols, which is the reaction with Grignard, we can react aldehydes with Grignard. The carbon attached to the metal in case of the Grignard reagent is carrying a partial negative charge. The carbon of the carbonyl is carrying a partial positive charge, and accordingly you will have an attack from the Grignard on the aldehydic compound, breaking the double bond, and then the product will abstract a proton from the medium to give the alcoholic compound. If the R that you have started with, this R, was a hydrogen, then you will end up with, which is formaldehyde. This means you have started with formaldehyde. Then this, you will end up with a primary alcohol. So only formaldehyde, when reacted with Grignard reagent, gives primary alcohol. If the R was a regular alkane, then you will have a carbon attached to two R's, two carbons, and then attached to an OH. So this is a secondary alcohol. So aldehydes can give primary or secondary alcohol when reacted with Grignard, depending on the carbon chain attached to the carbonyl. Whether the substituent attached to the carbonyl is a hydrogen, this will end up with the primary alcohol. And if it's attached to an alkyl chain, then you will end up with the secondary alcohol. So the primary alcohol is formed when reacting formaldehyde with Grignard. The secondary alcohol is formed when you react any other aldehyde with Grignard. Finally, if you react any keton with Grignard, if you react a ketonic compound with Grignard, again you will have the partial negative and the partial positive and an attack, breaking the double bond, and in such case you actually produce the tertiary alcohol. So to summarize, formaldehyde when reacted with Grignard gives primary alcohol. Any other aldehyde when reacted with Grignard gives the secondary alcohol. Finally, any keton when reacted with Grignard gives the tertiary alcohol. So as we said, we can prepare alcohols from alkenes by hydration, whether regular hydration or oxymercuration, demercuration. Both are Markovnikov additions. Or we can hydroborate the alkene, producing an anti-Markovnikov addition of a molecule of water, giving a primary alcohol. We can substitute a halogen in any alkyl halide using the hydroxyl group, giving the alcohol. We can use Grignard on carbonyl compounds like aldehydes and ketones to give primary, secondary, or tertiary alcohol depending on your starting material, as we have explained. Or you can reduce aldehydes and ketones and acids and acid derivatives. Aldehydes, when reduced, gives primary alcohol. Ketones gives secondary alcohol. Any acid or acid derivative will give a primary alcohol. So this is how you can prepare alcohols from their different starting materials. If we deal with the physical characters of these compounds, we will notice that they have an oxygen attached to a hydrogen, which means that the oxygen is more electronegative than the hydrogen, accordingly places a partial negative charge on the oxygen and a partial positive charge on the hydrogen. The container will contain more than one molecule of your compound, and accordingly you will have some sort of an attraction between the partial positive and the partial negative. This attraction is called a hydrogen bond. It increases the melting point and the boiling point by a value equivalent to what is needed to break the hydrogen bond. Again, they can produce a hydrogen bond with water. They can form a hydrogen bond with water. And accordingly, they are more soluble than their equivalents that cannot form this hydrogen bond. So they have an ability to form hydrogen bonds due to the presence of the OH group. So they can form hydrogen bonds with themselves, increasing the melting and boiling point, or they can form hydrogen bonds with water, increasing the solubility of these compounds in water. Finally, if we deal with the reactions of these compounds, if you remember, we said that you can prepare alcohols by 4 different methods. You had the alkenes, and you were performing a hydration. You had the alkyl halide, and you were performing a nucleophilic substitution reaction. You had the aldehydes and ketones, and you were performing a reduction, or in other words, you had the carbonyl compounds, let's put it correctly, all the carbonyl compounds, and you could reduce them to give the alcohols of your interest. The reactions of these compounds, the reactions of alcohols, is exactly the opposite of their methods of synthesis. For example, if you have an alcohol, you can dehydrate using conch sulfuric at 180 degrees centigrade. You will end up with the alkene. If you have an alcohol, you can halogenate using hydrogen halides or phosphorus trihalides or thionyl chloride to produce the halogenated compound. Again, if you have an alcohol, you can oxidize the alcohol to give the carbonyl compounds. But remember that oxidation of alcohols by a regular non-selective oxidizing agent will not produce the aldehydes. You can only produce the acids if you're starting with a primary alcohol, or if you're starting with a secondary alcohol, you will give the ketonic compounds. Tertiary alcohols are non-oxidizable. You cannot oxidize them. So these are the 3 different reactions that are the opposite of the methods of synthesis. You do not have to memorize both of them. Just remember either the methods of synthesis or the reactions, and the other one is exactly the opposite of it. One last reaction is the esterification, where you use the alcohol and you add a carboxylic acid to this alcohol in presence of few drops of conch sulfuric. You end up preparing your ester. So these are the reactions of alcohols. So as we have mentioned, the reactions of alcohols are exactly the opposite of their methods of synthesis. You can convert an alcohol to an alkyl halide either using a hydrogen halide, phosphorus trihalides, or thionyl chloride. And as we have mentioned before during the video of the alkyl halides, it's preferable to use the thionyl chloride because its byproducts are gases. So you do not have to purify your compound to a huge extent. It's already pure. You can convert an alcohol to an unsaturated compound, an alkene, using conch sulfuric by dehydrating the compound at 180 degrees centigrade. This is Zaitsev rule. Zaitsev rule says that when you are dehydrating an alcohol and you have two options for the position of the double bond, you can have the double bond either terminal or you can have it non-terminal. It's preferable to be non-terminal. Non-terminal are more preferable to terminal double bonds in case of dehydration. A double bond prefers to be more substituted. The more substituted the double bond, the more the probability of its formation. Now, back to the reactions. As we have mentioned, you can oxidize these compounds. If you're using a primary alcohol, you will have an aldehyde, but you will not be able to stop at the aldehyde if you're using an unselective oxidizing agent, and you will end up with the acid. A secondary alcohol will give a ketone and will stop at the ketone product. A tertiary alcohol cannot perform an oxidation reaction. Finally, the last reaction of these compounds is the esterification, where you react a carboxylic acid with an alcohol in presence of an inorganic acid under dry conditions, and you end up with the ester. Remember, you're using the conch sulfuric acid to shift the reaction towards the formation of the product, because there is an equilibrium between the starting and the final compounds. This reaction is it's not a straightforward reaction. It has an equilibrium between its starting and starting materials and products. It's a reversible reaction, and accordingly you have to add something that will absorb one of the products, which is the molecule of water. The conch sulfuric is added here to absorb the molecule of water and accordingly shift the reaction towards the formation of the products. This is according to Le Chatelier rule. You have to remove one of the products to shift your reaction towards the formation of more products. This way we have finished the lecture of alcohols. Next video will deal with the aldehydes and ketones.